Okay, so this should be the last of the log videos. As you can see, the title is Extra Rules, More Equations, and a bit more graphing. And so this will bring together absolutely everything that we could possibly want to talk about. So the first thing that I haven't talked about yet is the change of base formula. And so this is, there's no way around it. This is the change of base formula. What you can see happening here is the original input is on top, and the original base is on bottom, and what we've done is we have a totally new base, m, and that's going to be our base of choice. And so let me just quickly write a quick example. We have log base 3 of 12 can be written as log base 2 of 12 over log base 2 of 3, which could be written as log base 5 of 12 over log base 5 of 3, which could be written as, you could just keep doing this as many times as you want, log base 3/17 of 12 over log base 3/17 of 3. It doesn't matter. Whatever base you want, you can rewrite this as. And so you're always going to want to pick a base that's convenient for you. And so the idea is that you never know what base you may have a calculator for, but as long as you have a calculator that can handle a specific base, then you can pick that base by doing this change of base formula. So here is a couple of problems that use this. One, write log base 3 of 10 only using log base 5. And so we just do what we just did, which is the log base 3 of 10 equals, well, it's always log of the top over log of the base, and then this 5 is our new base, like that. And so the answer is log base 5 of 10 over log base 5 of 3. And that's our final answer. Write log base a of b only using base b. So let's do this. This is a little more esoteric because it's all in variables, but remember, just rewrite the b on top and the a on the bottom. Just like that. And remember, our new base is b. And here's an interesting thing that happens. If you remember, log base b of b is always 1. And so the top is 1. And the bottom is log base b of a. And so there's an interesting fact. If you switch the input and the base, you get 1 over the log instead, right? In the beginning, we started with taking base a of b, and here's base b of a, and it puts us in the denominator instead. So here's a really interesting thing that happens too. This little ditty up top, remember that anytime you have x, you can write it as either log base a of a to the x, or you can write it as a to the log base a of x. And this side, this here, is what we're going to use for answering the question that we have down here, which is x to the log a of y equal to y to the log a of x? Right? Can you somehow switch x and y in this equation? And so remember that x can be replaced with a to the log a of x, and because of that, x to the log a of y is a to the log a of x to the log a of y, and that's just a to the log a of x times log a of y. Now, whenever you multiply two things, the order doesn't matter. You probably remember that multiplication is commutative, so this is a to the log a of y times log a of x, which you can put parentheses here, is a to the log a of y times log a of x. Now, if we go back up top, a to the log a of anything is just the thing. So a to the log a of y is just y. And so we got the right-hand side of the equation, so the answer is yes. Well, that's super weird. So like 3 to the log 5 of 10 is just 10 to the log 5 of 3. And that's just an interesting thing that happens because of how logs and exponents work. So that's that, and let's look at a couple more equations that you might have to solve. So here, the thing you mostly want to remember is that log a of b equals c can be replaced with a to the c equals b. Right? So anytime you have an equation involving log like this, the thing you can do is change it to this equation. If one side has a log, then you can change it to this sort of equation. So here, we can change this to 3 to the 4th equals 2x minus 1. And then this is many times more manageable. In particular, 3 to the 4th is just 9 times 9, which is 81, equals 2x minus 1. And so 2x equals 82, and therefore x equals 41. See, that wasn't bad at all. So now here's an example where we're going to have to use a lot more sort of a lot more of the rules of log to help solve it. Since I don't have something like the previous situation here, where I can use that to write this, since I don't have that, right, see, there's not just one log, there's these two sides, I'm going to have to be more creative in my use of the log rules. So the first step I'm going to have to take is I'm going to have to subtract log 2 of x minus 1 so that my logs are on the same side. And what that gives me, well, first it gives me log 2 of 3x minus 7 minus log 2 of x minus 1 equals 1. And then you should notice that we're subtracting two logs with the same base, and in the back of your head you should be thinking log a minus log b is the same thing as the log of a over b. Right? And so since I'm subtracting two logs, I can just instead write the log of the first divided by the second. Now, we can use our highlighted rule, right? We're going to go ahead and replace this with 2 to the 1 equals 3x minus 7 over x minus 1. And so we have a fraction equals 2. We can just multiply both sides of this fraction by x minus 1. So both sides of the equation we multiply by x minus 1. Here the bottoms cancel, and we get 2x minus 2 equals 3x minus 7. And if we bring this over, we get x equals 5. Now it's important after you get your answer, right, because you've just done some magic, you should check to make sure your answer makes sense. And so if we come up here, log 2, 3 times 5 is 15 minus 7 is 8, equals 1 plus log 2 of 4. The main thing you want to check is when you plug in your value of x, that none of the logs are trying to be logs of negative numbers. If any of these were negative, we would have to reject it. And what's important is that that's 3, and that's 2, and 3 does equal 1 plus 2. So again, since neither of these were negative, we didn't have to reject, and indeed you can check it does work out. So there's an answer to a question involving some logs. Again, let's solve one more time for x so we get practice. Here we have an expression up top that we want to isolate the x in, and we would love to bring that down. And the way to do that is to just take log of both sides, and so we take log of both sides, and we choose a base. Remember, we have to choose a base. And the base I like to choose is the one that kills whatever is closest to the x. And so we get 2 minus x times log 3 of 3 equals log 3 of 10. That is just 1, and so 2 minus x equals log 3 of 10. And if we just add x to both sides and subtract log 3 of 10 from both sides, then what we wind up getting is x equals 2 minus log 3 of 10. Now, I want the answer to look nicer than that. And so I'm going to come up here, and I'm going to note that 2 is the same thing as log 3 of 3 squared, which is log 3 of 9. And so if x equals 2 minus log 3 of 10, then x equals log 3 of 9 minus log 3 of 10. And since we're subtracting two logs with the same base, we can just write it as log 3 of 9 divided by 10. And so one way you can make your answers look nicer is by changing your numbers also into logs so they can all be combined together. Alright, so here is a random logarithm question. The formula for the half-life of an element is given by a of t equals a0 times 1/2 to the t over t0. And so here are some things. a0 is the initial amount, t0 is the half-life. And then a of t is just a function of time. This is the current amount. Right? So A of t is just how much is left after time t. And you can see where the variable shows up here as an exponent. And so down here is a question that I could possibly ask, which is, if the initial mass of a compound is 100 grams, and it has a half-life of 8 days, how long is it until there is only 10 grams left? And so here you have 100 grams. That's your A0. Here you have 8 days as the half-life. That's your T0. And 10 grams left, that's just your A of t. And so identifying the pieces that you have will help you in solving this question. So let's go over to the next page. Here I've set up the equation. A of t equals 100, right, there was your A of 0, times 1/2 to the t over 8, 8 was your T0, and we want A of t to be 10. And so we get 10 equals 100 times 1/2 to the t over 8. Now, to solve this, first we want to get this by itself so we can take log of it to pull the exponent down, right? This can come down if we can take log. So, first step is to divide both sides by 100, which gives us that 1/10 equals 1/2 to the t over 8. And then we just take log of both sides, log of 1/10 equals log of 1/2 to the t over 8. And then remember, this will just come out front. So we get log of 1/10 equals t over 8 times log of 1/2. And so solving for t right now is actually really easy. All we have to do is multiply both sides by 8 and divide both sides by log of 1/2. So multiply by 8 and divide by log of 1/2. And then you just get t equals 8 log of 1/10 over 8 log of 1/2. And we, there's no 8 in the denominator, sorry. Now, log of 1/10, log of 1 over a is equal to negative log a. So the top becomes 8 times negative log 10 over negative log 2. And then my negatives, both of them, since I have a negative up top and a negative down below, they cancel. And I just get 8 log 10 over log 2. And if you plug that into a calculator, you actually get that this is, I guess equals isn't right, is approximately equal to 26.58 days. And so if you have a half-life of 8 days, then after about 26 and a half days, you'll have 1/10 as much as what you started with. And so that's a way to handle a half-life question, which is totally something you guys can now handle, given that you understand logarithms a little bit better. Alright, so just really quickly, we do need to do a couple of extra types of graphs. Remember that the quickest way to graph a new function is to use an existing function you know and apply transformations. And so here's your quick review of transformations. The original graph, right, this is the original, can become the new graph under transformations, right, so this is the new graph, if we can identify these A, B, C, and D by using this amazing chart. This amazing chart tells you to take the x values and first multiply them by 1 over b, and then add negative c over b. Take the y values, multiply them by a, and then add d. We must always multiply first and add second. This will give us the exact transformation each and every time. And so if I want you to graph y equals 1/3 of 2 to the x minus 3, then the main graph you should be basing this off of is just 2 to the x, right? There's the 2 to the x, but then there's all these crazy transformations happening. And so if you write a2 to the bx plus c plus d, and you write 1/3 2 to the x minus 3, right? This is the one you want to graph. And we need to identify the a, b, c, and d. Then you have, it's really straightforward to see that the a has to be 1/3, the b is 1, the c is -3, and the d is 0, right, to make this work out. And so if we make the table, right, this is multiply, this is add, this is x, this is y. We're going to multiply the y values by 1/3. We're going to add 0 to them. We're going to multiply the x values by 1 over 1, which is 1, and add negative c over b, which is 3. So we're going to add 3 to all of the x values, and then we're going to multiply all the y values by 1/3. And so if we were to normally graph, right, if we were to normally graph 2 to the x, we would make a little chart, x, 2 to the x, and we would plot some values. For example, we would do 0, 1, 1, 2, 2, 4. And the way you can go from this table to this table is by doing what it says to the x values and doing what it says to the y values. So we're going to add 3 to all of the x values, and it's going to give us 3, 4, and 5. And we're going to multiply those y values by 1/3. And so it's going to give us 1/3, 2/3, and 4/3. And so if we come over to our graph, 1, 2, 3, 4, 5. If we were to graph the original function, which I'll do here in that green, right, we have 0, 1, we have 1, 2, and we have 2, 4, and there's our original 2 to the x, and now all you have to do, right, is take these points and put them on the graph. So if I divide into thirds, here's 3 1/3. Right? This point is just there. 4 2/3 is here. And 5/4, let's add some more thirds. 5/4 is here. And so now we just connect these. Like that. And here's the graph of y equals 1/3 x, 2 to the x minus 3. So here's another one. Graph y equals 2 log 2 of 1/2 x plus 1. And so your goal is to write a log of bx plus c plus d, and to write 2 log 2 of 1/2 x plus 1, and to figure out all of the values. Well, a is 2, b is 1/2, c is 1, and d is 0. And so if we make our table, right, multiply, add, x, y, we multiply by 1 over b, which is 2. We add negative c over b, which is negative 1 over 1/2, which is negative 2. We multiply the y values by a, which is just 2, and we add d, which is just 0. So normally, when we graph log 2, right, we normally would pick maybe 1, 2, and 4, 0, 1, and 2. Right, here's our normal coordinates. And let's just go ahead and put those on the graph. So there's 1, 0. Here's 2, 1. And here's 4, 2. And there's our normal graph of log 2 of x. Well, remember, to get our x and our y for our other function, we just use this table here. So we're going to take every x value, and we're going to multiply by 2 and add negative 2. So 1 times 2 is 2, minus 2 is 0. 2 times 2 is 4, minus 2 is 2. And 2 times 4 is 8, minus 2 is 6. And then to our y values, we're going to multiply by 2 and add 0. And so 0 times 2 is 0, 1 times 2 is 2, and 2 times 2 is 4. And so we'll graph these in orange. 0, 0 is on our graph. 2, 2 is on our graph. And 6, 4 is on our graph. And one important thing that you should note is that normally on our original graph we have an asymptote here at 0, and the new graph, if you multiply 0 by 2 and subtract 2, you get negative 2, so the new graph has an asymptote back at negative 2. Let me do that in orange. Has an asymptote back here, and so when you go to connect these points, you want to get closer and closer to that asymptote, and then here's the graph of y equals 2 log 2 of 1/2 x plus 1. So this is a very long video. I'm sorry that it's actually so long. But what we did was we dealt with change of base, we got to play with some really fun equations, and we got to graph some transformations of both exponent and log. So it may be a long video, but it does cover everything else you need to know. Please go ahead and watch it, digest it, do the homework, and I will see you in class.